looks like we need to cover a lot of things. Also, I'm going to add a problem. I'm going to add a 12.5 to that.
What?
So that the z-substitution. So we're going to add, first of all, add this to the list of integrals that you got to do. 12.5. Who knows? Maybe we might have to spend 3 days on this the way rate we're going.
Yes. I agree.
Yes.
So 12.5 integral dx all over cosine x plus sine x. Now, in order to do this problem, you have to do what we call a z-substitution. But we'll talk about that later.
Hey.
We gotta worry about problems 1 through 7. Or at least 1 through 6. And then we gotta make sure we all get the answers, because then we need to post the answers. So let me get a piece of paper here to write them down. Okay, can we agree on the answer for number 1?
2/3 tangent cube.
Let's see.
2/3 tangent cube
root x.
root x
Plus c.
plus c. Everybody agree on that, Joe?
Oh, I didn't get that, but it's like probably wrong.
Okay, so in number 1, if
Wait.
you let u equal to tangent root x, du is equal to secant squared root x times 1 over 2 root x dx.
Wait, what?
U substitution, this is like the simplest thing.
Did you get it?
And so then, the integral becomes u squared times secant squared times 2 du. So that's going to be 2/3 u cubed plus c. And then if you substitute back in, yep, that is the correct answer. Joel? Let me write this down. So future classes can have answers 2/3 tangent cube root x plus c. Okay, what about number 2?
3/10.
3/10?
Yeah.
Yeah. Oh, I got you.
I got d over 5 plus c.
Oh my,
Oh.
there's no plus c if it's a definite integral.
Oh yeah.
Did you get 3/10?
Oh my goodness. Okay, it looks like we have.
Oh yeah, no.
Are we gonna end up doing them all?
It's
Maybe
C10.
we should
It's
do
C10.
it.
It's C10. It's C10.
Because the derivative of cosine is negative sine? Was that the problem? Let's
Wait,
just do
did
it
you
for
get
the
more
video.
plus minus?
Integral from 0 to pi over 3 sine 2x dx. If this was the case, I should have just made an answer key.
Yeah.
I mean, I should have just wrote all this, done it on a piece of paper and then like,
No, let's do it.
and post it,
Yeah.
if this is the case. Would have saved me a lot of time, I think, and you a lot of time. 1 plus cosine squared x, is that correct? Squared, squared. So, u equals 1 plus cosine squared x, did you guys do that? Du is equal to 2 cosine x times negative sine x dx. So this integral becomes u squared on the bottom, and sine 2x, of course, is the same thing as 2 sine x cosine x, which is this part right there, which is negative du, and your new limits of integration are going to be, if you plug in 0 here, you get 1. What?
Wait, you mean
You
2?
get 2, I thought.
Oh yeah, 2. And if you plug in pi over 3, you get 5/4. So you get negative, and the integral of this is negative 1 over u, so it's positive 1 over u from 2 to 5/4. So you will get 5, 5, I'm going to do this quickly, minus 1/2, making a least common denominator. Not
You know,
5/4,
you
it's
flip
4/5,
it,
it's
yeah.
4/5. 4/5 minus 1/2, so making a least common denominator of 10, you get 8 minus 5, so the answer is 3/10. What's going to happen on the test? Pain. Is that what's going to happen? Number 3. Okay, can we agree on the answer for this one?
Oh no, you couldn't get it.
You couldn't get it?
Because I got
X.
stuck.
X.
Okay, so this looks like integration by parts just by looking at it, yeah?
You can't tabulate.
No.
Okay, let's try tabular. X, 1, 0, and then in this column, you have to anti-differentiate. What's the
Oh
anti-differentiate?
yeah, yeah. That's right.
Okay, no, cannot do tabular. Oh boy. So, integration by parts, u du dv v. You know what? Maybe after lunch, I have 2 free periods, maybe I'll just make the answer key for the whole darn thing and post it.
Wait, sorry, I'm on, so on number 2, you know how you have the negative in the integral of,
Because of this, right?
yeah, so that's on the next step,
Yeah.
and then like how.
Oh, but
how
it
does
changes
go
to,
there?
because the integral of 1 over u squared is negative 1 over u, yeah?
Okay,
And so negative times negative is equals a positive.
yeah.
Say it, a negative times a negative equals a positive.
Negative
Yeah.
It actually said.
You guys remember that from the movie last year?
Yeah.
Cho probably doesn't because you weren't even paying attention yet.
Why?
So tan inverse x goes there, x dx goes there, so this is 1/2 x squared, and that's gonna be 1 over 1 plus x squared dx. Did I do that correctly?
Yes.
So this integral is equal to uv 1/2 x squared tan inverse x minus the integral of v du, so that's gonna be 1/2 x squared dx all over 1 plus x squared. So this problem hinges on whether you can do this integral. Did you get that far?
Yeah.
And what happens when the degree of the top is not smaller than the bottom?
You can,
Long division.
yeah.
So x squared plus 1 goes into x squared 1 time, x squared plus 1, subtract. So this becomes 1/2 x squared tan inverse x minus 1/2, and then, so if you do the division here, you get the quotient plus the remainder over the divisor, and then now you can just take it home, right?
Isn't there an integral sign?
Oh yeah. So, 1/2 x squared tan inverse x minus 1/2 times the integral of this, but that's easy. X minus tan inverse x, and then don't forget to put the plus c. I just did the whole darn thing. 1/2 x squared tan inverse x minus 1/2 x plus 1/2 tan inverse x plus c. So can we agree on that one now? Yeah, no, I did the whole thing. No, for real, maybe I should.
Yeah.
Maybe I should start now already. Because then I'm gonna have to do it twice. That's okay. That's what I get paid the big bucks for, right? Number 4. Now, a lot of you had trouble in this one. I'm not going to finish it for you. Oh, I probably will. Dx over x cubed plus 8. So obviously, this is like a partial fractions just by looking at it already, right? So dx all over, if you factor the denominator, you get x plus 2 times x squared minus 2x plus 4. Correct? And then if you do a partial fractions on this, 1 over x plus 2 times x squared minus 2x plus 4, that's equal to a over x plus 2 plus bx plus c all over x squared minus 2x plus 4. Did everybody do that? Okay, what did you guys get for a, b, and c? What is it? You get, just tell me what.
1 over 12.
1/12. What is b?
Negative 112.
Negative 1/12. Then what is c?
1/3.
1/3. Okay, I trust you. So this integral becomes negative, no, 1/12 over x plus 2 plus negative 1/12 x plus 1/3 all over x squared minus 2x plus 4 dx. Shall we just factor out a 1/12 so that we don't have fractions? Okay, so 1/12, I mean, you don't have to, 1 over x plus 2 plus negative x plus 4 all over x squared minus 2x plus 4 dx. Okay, now this integral is easy, right? That's going to be natural log absolute value x plus 2. But how do you do this integral? What do? You do a trig substitution. So what you have to do is you have to like complete the square here, x minus 1 quantity squared plus 3. Complete the square. And then see, that's a perfect candidate for trig substitution. So therefore, you just let x minus 1 equal, which one is this, the sine, the tangent, or the secant one?
Tangent.
That's plus the tangent. So root 3 tangent theta. So therefore, dx would equal root 3 secant squared theta d theta. Trig substitution.
Hey, so the x minus 1 is like the x in the trig substitution?
Exactly.
Okay.
Yeah, so it's like x squared, except it's x minus 1 quantity squared.
Oh, so the x is whatever like is like being resued. Okay.
Can you guys finish it? Or do you need me to finish it? I am gonna finish it. I'm gonna post it already. I made up my mind. After lunch, I will sit down at my desk for 1 hour and grind it out. Come on, you guys were supposed to do this. Like last year, you know what our Shiro did every time? Look it up on Wolfram Alpha. That's what he did. Are you guys doing that? I mean, just to check your answer.
I don't know how to use that.
You go to Wolfram Alpha and then you just punch in the integral. And the thing spits out the answer.
How do you get the integral sign?
I think they have like.
Yeah, I think. Okay, we don't have to do number 5, right? Number 5 is tabular. Did everybody do tabular? Okay, tell me the answer.
Negative 5 fourths times 4. Negative 5 over 4e squared.
Everybody got that?
No, okay.
Oh, okay.
What did you get?
Looks like we gotta do it.
Wait, I just
Integral
have
from 0 to 1, x squared e to the negative. So as soon as you see this problem, you gotta be thinking, I'm gonna do tabular. X squared 2x to 0. This one you anti-differentiate, so it'll be negative half e to the negative 2x. 1/4 e to the negative 1/8 e to the negative 2x. Plus minus plus. So you're going to get negative 1/2 x squared e to the negative 2x minus 1/2 x e to the negative 2x minus 1/4 e to the negative 2x. And since we have limits, 0 to 1, plug in the top number and you get negative 1/2 e to the negative 2 minus 1/2 e to the negative 2 minus 1/4 e to the negative 2 minus, if you plug in 0, 0, plus 0 minus 1/4. So your final answer is going to be negative 5/4 e to the negative 2 plus 1/4. Joe, you got
I
that?
got that.
Shall we just make the least common denominator? Let's leave it. Leave it already! Why am I even writing this on if I'm going to do the whole thing anyway? 1/4 minus 5/4 e to the negative 2. Wow, what kind of mistakes are we making?
I didn't have it 1/4.
You just assume when you plug in 0, you get 0.
No, forgot.
Okay, what about the next one? That one we can do, right? Solving for the unknown integral? In fact, probably going to get that one on the test, but instead of cosine, I'll put sine.
I tried, but I'm.
Boo! Okay, when we solve for the unknown integral, we need room. You know, instead of spending my time doing this, I'm just, never mind, just do it. Just do it. Integral e to the ax cosine bx dx. So, you know you're going to have to do it twice and you got to bring it over, right? So, u du dv dv. So, I'm going to make u equal to the exponential. I put the trig function over there. So, this becomes a e to the ax dx. And this becomes 1 over b sine bx.
Yeah.
We got that?
Yeah.
Okay, so I'm going to call this oval. oval is equal to uv 1 over b e to the ax sine bx minus the integral of v du. So that's going to be a over b on the outside, e to the ax sine bx dx. So now we got to do this integral, which I call box. So then you do the same thing, u du dv v. So e to the ax, a e to the ax dx. This is sine bx dx, so it's going to be negative 1 over b cosine bx. Did you get that? So the box is equal to uv, negative 1 over b, e to the ax cosine bx, minus the integral of v du, so that's going to be plus a over b, e to the ax cosine bx dx. But that's oval, that's the original integral. That's what's supposed to happen here. So oval, so if you put it all together, is 1 over b e to the ax sine bx minus a over b times all of this. So it's going to be plus, what's negative a over b times this? A over b squared. E to the ax cosine bx, and then negative a over b times this going to be negative a squared over b squared oval. But then you got to bring this over on this side, so what is that going to be? What happens if I bring this on this side? I'll give you a hint. This is b squared over b squared oval. So if I add it, you can get, add that to this side. Come on, I'm not going to do everything. Add it on this side. A squared plus b squared over b squared oval is equal to 1 over b e to the ax sine bx plus a over b squared e to the ax cosine bx. And then now all you have to do is multiply both sides by this, by the reciprocal of that. So oval is equal to b squared over a squared plus b squared times 1 over b e to the ax sine bx plus a over b squared e to the ax cosine bx, and then don't forget to put the plus e. And actually it looks much nicer if you distributize that. So if you distributize that, you get b over a squared plus b squared e to the ax sine bx plus a over a squared plus b squared e to the ax cosine bx plus c. Woo! That was fun.
Wait, let's start. Like, how do you figure out that e to the x is u?
It doesn't matter. You could have put cosine bx there and put the e there. But when you do it the second time, you have to keep it consistent. That's what we were talking about last time, right? If you put the exponential function there and the trig function there, when you do it again, you got to put the exponential function there and the trig function there. Or you could put the trig function there, exponential, but when you do it again, then you got to put the trig function here and the exponential there. You just got to keep it consistent. Okay, let me write down this answer. So on the test, what I'm going to do, change it to e to the ax sine bx, yeah? And what's going to happen? All hell's going to break loose. Park? Oh, you know what? You know what I'm thinking for you guys? Maybe we need to plan the test on an extended period.
Yeah.
Because we're laboring with integrals. E to the ax cosine.
Wait, when's the next extended though?
I have no idea.
Let's
I can look
check.
it up on the calendar.
It's on Tuesday, September 5th.
Oh, that's a good idea.
It's in,
That's pretty close, yeah?
Yeah,
it's
very
in,
close. Yeah, actually,
two
I
weeks.
exactly.
A week and a half.
Maybe. Maybe we're gonna have to go to plan B already.
So you're gonna combine like.
Okay, that's 1 through 6 now. Problems 7, 8, and 9 are all trig substitution. So did you guys even try any of them?
I did 7.
Yeah, I just said.
Okay, what was the answer? Did you guys tell me?
Natural log of absolute value of secant theta plus tan
No!
Well, yeah, I
If
got
the
that, but, like,
original-
you have to like change it.
Yeah, but if the original problem is in x, you gotta leave your answer in terms of x.
Oh.
You gotta
Oh,
change
so
the
you draw a
thetas back to
triangle.
x's. Yeah, by drawing the triangle. Okay, Cho, tell me your answer for number 7 and let's see if everybody else agrees.
Natural log x over 2 plus square root of
There's no
x.
absolute value.
Oh yeah, there is. I mean, like, yeah.
Okay.
It's the square root of x squared minus 4 over 2 and then plus c.
Wait, how you
Jason, you got that too?
I got 2 over x squared minus 4. I just got that flipped, so it's probably a mistake on that.
What about Park?
Wait, how do you draw the triangle?
Let's just do this bloody problem. I gotta teach you about the z-substitution too, you know. Because otherwise we're gonna be a bit fuddled. Number 7.
Yeah, he's definitely right. I messed up.
dx all over x squared root of x squared minus 4. And then I give you a, you know why I give you a restriction like this? So that you don't have to worry about absolute values. Because otherwise you're gonna make a piecewise function. Okay, so this one, did everybody go x equal to secant theta?
Yeah.
Dx is equal to 2 secant theta tangent theta, d theta. And then so this integral becomes 2 secant theta tangent theta d theta all over the square root of 4 secant squared theta minus 4. But that is, if you factor out the 4, is 4 secant squared theta minus 1. But hey, you somebody, that's 4 tangent squared theta. Okay, now, what is the square root of 4 tangent squared theta? It's 2 times the absolute value of tangent theta. However, because of that restriction, see, that's what I mean, you don't have to worry about the absolute value. The 2's cancel out, the tangents cancel out. Hey, that's on the list. Let me test somebody. Huh? Integral of secant theta.
L and absolute value secant theta plus tangent theta
Plus c.
plus c.
Okay, now, how do you change it back? You go back to your substitution and draw the triangle. Isn't this the same thing as saying secant theta is x over 2? If you move the 2 on this
yeah.
side. So then secant theta is x over 2. Hypotenuse over adjacent. And then you use the Pythagorean theorem. So that's going to be the square root of x squared minus 4. Oh, what a surprise! That expression is like the one in the integral. Whoa! That's not a surprise. So, natural log. So looking at the triangle, secant theta is hypotenuse over adjacent, plus tangent is opposite over adjacent. Okay, this is the correct answer. However, come on, we're above BC calculus now. So this should be your final answer. Natural log absolute value of x plus the square root of x squared minus 4 plus c. That should be the final answer. Mr. Park, what happened to the 2? Park, tell me what happened to the 2. Okay, think about that.
Oh, I got it.
Okay.
You factored it out and then it goes in constant.
Very good. You guys understood what he said?
Wait,
You can just put it in.
Natural log 2 is a constant. Incorporate it into the plus c. You guys know
would you
what?
mark it wrong if we did like our original answer?
Oh, I wouldn't mark it wrong, just take off points.
Oh.
See? Okay, look. This is for the video. Natural log, isn't this the same thing as x plus the square root of x squared minus 4 all over 2 plus c? And then using your properties of logarithms, isn't this the natural log of the absolute value of x plus the square root of x squared minus 4 minus the natural log of absolute value 2 plus c? But since that's a constant, you just mush it together and just get 1 plus c. You incorporate it into the constant. Natural log 2 is a constant. Which is approximately, Cho? Natural log 2? Give me 3 decimal place accuracy. I told you guys this.
0.871.
No, 0.693.
When it's
Yeah.
Where did that come from?
Just random.
All right. See, that's the kind of the tricks of the trade that you gotta know. Okay, so did you guys stop at number 7?
Yeah.
I tried to do number 8.
Okay, did you do trig substitution?
Yes,
Yeah.
X equal 3 sine theta?
yes.
And then just take it from there.
You get just X.
Not too many things
Yeah.
cancel. There's an x squared on the top too, you know. Okay, you guys work that out, and I'm gonna. Okay, so let me teach you about the z substitution, and we're done. And then I'm gonna start making the solution key. I should have done this earlier. I should have known. I'm the stupid one. Oh, it would have saved me a whole bunch of time if I just made that as key. So that means, but I'm not gonna do it for the next assignment, which is the powers of trig functions. You guys are gonna do that now. Or maybe I should. I don't know. Okay, so anytime you have a rational expression with sine and cosine, like the problem I gave you, 12.5, dx over cosine x plus sine x. See how it's a rational function in terms of cosine and sine? We can use the z substitution to transform this integral into a doable integral. Good. So here's this is called the z substitution. Z equals tangent x over 2.
Is it always?
Yeah, that's the z substitution. So the z substitution will transform any rational function in terms of sine and cosine into a rational function.
Wait. What does that mean?
You know what a rational function is, right?
Yeah.
It is something polynomial over polynomial. So if you think of cosine x and sine x, just the variables, this is a rational function, right? This is like u plus v, how's that?
Okay.
Okay, but so if you do the substitution, substitute it in, you're gonna get a doable integral. Okay, so what do you do with this? Well, what you have to do is, we need to substitute something for cosine x, sine x, and dx. That's what has to happen. So, using this substitution, what we need to do is we need to derive formulas for cosine x, sine x, and dx. Okay, now, to do that, all you gotta do is use some trig identities. Anybody?
Huh?
Okay, z is equal to tangent x over 2. Now, tangent x over 2, there's 3 identities. Which one do you think I'm going to use here? You can use any one you want.
Sine x.
Tangent x over 2,
Oh, I
sine
forgot.
x, that's not an identity.
Oh my.
Sine X over 2 equals sine X over 2.
Not that one either.
It's-
I'm talking about the half angle identities. Okay, here, I'm gonna tell you which one we're gonna use. Plus or minus the square root of fill in the blank part.
Oh,
Redeem yourself.
1 minus cosine x over 1 plus
Very
cosine.
Yeah, yeah.
good. Now, can you use this equation to solve for cosine x?
Sure.
Yeah, and that's what we're gonna do. So square both sides. Z squared is equal to 1 minus cosine x all over 1 plus cosine x. Cross multiply. Z squared plus z squared cosine x is equal to 1 minus cosine x. Isolate the cosine. Z. Can we do this all in one step? Let's just do it. Put all the cosine x's on one side. So z squared cosine x plus cosine x. Put everything else on the other. 1 minus z squared. Factor out the cosine x, and you get z squared plus 1. Can you guys see it already? So therefore, cosine x is equal to 1 minus z squared all over 1 plus z squared. Bam! Let's write it here. 1 minus z squared all over 1 plus z squared. Now, I'm going to give you a problem like this on the test, so if you want to like reinvent the wheel and derive it, you can, but you know, if, like when you go to college next year, you're going to enter an integral contest.
Yeah, sure.
It might be helpful if you just have these memorized instead of like deriving it every time.
Are you gonna make us derive it on the rest?
No!
As like
Well, it's up to you what you want to do. I'm just going to give you a problem. If you can't do the z substitution, then But come on, gonna do it, we're gonna do it on extended then. So instead of 55 minutes, you're gonna have 70 minutes. People used to do this test, you know, in the old days, they used to do it in the old period. Even a basic period, the longest was 45 minutes.
Oh,
Wait, where does z equals tangent x over 2?
That's the substitution.
Are you kidding me?
It's
Just give it.
No, you have to know that. Or you can just memorize these three right here.
Oh, so
If you just memorize these three, but this is how this is derived. I'm deriving it for you.
It's always that then.
Yeah, it's always that.
Oh, okay.
And it's always gonna be this. Now, once you have cosine x, how do you get sine x? Because there's no identity for tangent x over 2 that only has sines in it, right? Remember what the other two were?
Oh, do you
You guys don't, oh no.
triangle?
No, you know what? You guys are supposed to know. What are the other two identities for tangent x over 2?
Oh. It's a root.
1
minus cosine x
over,
sine x.
okay, and the other one is sine x over
1
1 plus cosine x.
Oh.
Remember the half angle? See, but there's no identity that only has sine in it. See, like this one only had cosine, so we could solve for it. So there's none that has only sine in it.
You plug it in. Cosine x.
So the easiest way to do it is draw a triangle. Go. Cosine of angle x is this over that. So what is cosine? Adjacent over hypotenuse, right? Using the Pythagorean theorem, wouldn't this side be the square root of this squared minus that squared? Yeah? Okay, now, since we're high-level mathematicians, can we do that in our head? Okay, let's just multiply it out. 1 plus 2z squared plus z to the 4 minus 1 plus 2z squared minus z to the 4. The 1's cancel out, the z's to the 4th cancel out, so all you have is the square root of 4z squared, which is
2z.
2 times the absolute value of z, but assuming z to be positive, I guess we kind of have to. You get 2z. So therefore, sine is opposite over hypotenuse. So 2z all over 1 plus z squared. Okay, now how do we get dx now? One last thing and we're done. How do we get dx? I'll give you a hint. Look at this.
You integrate.
No, you gotta solve for x. You need, no, we're not integrating. We're gonna take the derivative. See, like if you had x equals something, then it's easy to find dx, right? The derivative. So, how do you solve for x? What's the first thing I should do?
Try, oh wait, no.
And we're solving for x. This is just using algebra.
Inverse?
Tan inverse both sides. So tan inverse z is equal to x over 2. X is equal to 2 tan inverse z. So therefore, what is dx? What's the derivative of that going to be? 2 times, what's the derivative of tan inverse z? 1 over 1 plus z squared dz. There you go. Is that easy to memorize? Yeah, I think you can. Because I don't want to derive this every time. I would rather want to memorize that. So, if you take these things here and plug it into this, I'm not going to do it for you, then you're going to get a doable integral. You should get a doable integral. This is called the z-substitution. When do you use the z-substitution again? When you have a rational expression involving sines and cosines. Just like this. I'm going to write this down so I don't have to derive it again. Used to be in the calculus book, but apparently they took it out. This was fun. This, you know, in the old days, like 20 years ago, this used to be in the regular course
Or
For
for BC. But now it's like optional. See, and even trig substitution. Trig substitution is not on the AP exam anymore either, yeah?
Oh, really?
Yeah, it used to be for BC, but now it's not. The only thing you have to do is partial fractions. You just have to do integration by parts and partial fractions on the BC exam. So it's watered down. In fact, you know what? If you look at an AP exam in the 1960s and 70s, it's harder than the BC exam now. I wonder why. Video games,
Cho.
iPhones,
I don't have it.
or whatever, what do you call smartphones? Whatever they are. Microwave ovens. No, I had microwave ovens back then. No.
Since when?
When I was in elementary school, there was no microwave oven.
I do pizza.
What's your smart?
Put it in the regular oven. We just had a regular oven and a stove. There was no microwave oven. Yeah. That's it. All right, so we're gonna finish this up. So yes, after lunch today, I'm gonna sit down at my desk. I'm gonna make the solutions for the whole thing, and then I'll post it on the website. Solutions for the integral review. And I hope you guys just don't copy it, because you know what's gonna happen on the test. Pain.
Wait, so are you?
Even though we're gonna do it on the extended then. Yeah.
Are you taking 3 days for
Oh.
homework or
What?
just so that tomorrow? The homework.
Okay, let's look at the assignment sheet then.
Wait, if we're doing an extended, are we just doing an integral test or like integral plus factors?
Say that again?
If we're gonna do it in like another 1.5 weeks, is it gonna be just integrals on the test? Or?
No, it's only gonna be integrals. I have 12 integrals on the test. So when is the first extended? Where does it say?
Fifth.
On the 5th.
Well, when was the test? Oh, we only postponing it 2 days.
Okay, let's
Oh.
Okay, let's just change it right here then. Oh, but look, the 5th, oh, you mean the 6th then?
do it. Oh, yeah.
So here, get rid of this, and just put it here. Hey, what happened? Ah!
Wait, but what's with the colors?
I don't know what I'm doing.
Colors are.
No, you.
Look, they're not all separated by subject, because vector is also different.
Say that again?
How come we have different colors?
I don't know, this is just the way it came to me.
Oh,
So then,
Oh, I bet it's the cycles. Like
the
the.
cycles.
A, B, C,
Oh, the
D.
yellows are the extended, then
Yeah.
the pinks are the wait,
Next one?
pinks and the greens.
A, B, C, D. But then A, B, C, D is like 2 cycles is 1 color.
Yeah, and
A,
then.
B,
Oh,
C, D.
that makes sense.
Oh, A, B, C, D, A, B, C, D.
Yeah.
And then extended, and then A, B, C, D, A, B, C. Oh,
Wait,
this makes
wait,
more
then how
sense.
come this one is green and this one is purple?
They're confused.
But then over here, it's
It's always-
green and green.
Oh,
Because there's
they're
no
not
extended.
Yeah.
What?
It's just counting the time
There's no
until
extended.
extended.
God, why don't we have
Wait, where'd you get this from?
Mr. Ye?
Oh.
Mr.
No, he sent it to all the teachers to, if they want to use it. So I thought, oh, I'll try it this year and see what happens.
Oh, I
Why,
thought
this
you
is better
made it
than the assignment
yourself.
sheet I made last year?
Yeah, way better.
The one just listing it up.
Yeah.
Well, I don't see what's wrong with that. Okay, so see, that's why I don't want to go too far because we got to go to plan B how many times? So, shall we just do, how many, you know what then? Here, I just thought of something. We just do this then. We spend 3 days on this, 3 days on this, and 3 days on this then. 3 days on each one. That's nonsense. There, how's this then?
Yeah.
How does that look? 3 days on the integral review worksheet and 3 days on integrating powers of trig functions.
Wait, when is the second homework due?
On the day of the test, September 6th.
Everything's yeah.
Everything's
Oh,
due.
there's a holiday.
Everything's due on the day of the test.
Wait.
Woo! I like that.
Okay. I mean, I can't do better than that.